If you have to go, I'm getting college, not paper to vote.
Hey guys, these next 2 days are gonna be a little bit cramped here, so I want to spend 20 minutes going over the new material, and I want to spend the last half of class doing some more calculator work with you, okay? In preparation for Friday's test. So let's go to notes for today. So we've done logs and exponential functions from a derivative standpoint. Now we're going back to chapter 5 and doing the integral perspective or the antiderivative perspective. So let's say we have this problem 1 over x dx. What would happen if we attempted to apply power rule for this problem? First, you would have to make what adjustment? Right. First, you have to make what adjustment? Yeah, bring x up to the top. If the x up comes up to the top, what does it become? X to the -1 dx. Okay, so let's attempt to do power rule with this problem. What do we get? X to the 0 over 0. What's the issue? Can't divide by 0. So this is the one case that power rule fails, because any other power, we can avoid that 0, right? So this is the only instance where power rule is not going to work. So we have a workaround for this particular integral problem. Okay. So if you remember from first semester, we learned that the natural log used derivative is u prime over u. So anything that is in this form, if you're just to imagine this as du over u, then the antiderivative should bring us back to natural log of u. So that's the connection here. So the rule for 1 over x dx is going to be natural log. So the 1 over u is a more general form, but natural log absolute value of x plus c. So this is what we're working with today. Okay. If it's any other power, like x to the -2 or x squared or x to the 3/4, we go through power rule. But in this one instance, because power rule fails, we have a natural log rule to handle this one specific case. So let's look at example 1 here. Take the integral of 2x over x squared plus 1. We learned from a previous section that if I only had one term in the denominator, I could find a way to bring that term up to the top and just rely on power rule. But as soon as there's more than one term in the denominator, we have to look for a more involved rule. So in this case, it looks like we're going to need to rely on u substitution. Okay. So what could be a u value that we could use? If you had to guess. Yeah, it's going to be the entire denominator, x squared plus 1. Usually we want our u value to be a significant portion of the problem. And if we let that entire denominator be x squared plus 1, that should help clean up and sort out our problem. And what's nice about this degree, x squared, is 1 higher than this x up top. So that should end up giving us a nice pairing. Okay, cross multiply. Oh, and I forgot to do this. Whenever I did the u value, I want to always focus my attention on what I want to replace first. Right, so a lot of carryover from previous student. All right, do the x's go away? Yes, so whenever we do u substitution, we need the x to go away. Just so happens the 2 also goes away. So I'm left with du over u, but I can make it match my rule. So we know this is not power rule, right? If it's u to the first power in the denominator, we know it's going to run into this issue of failing if we push it to the numerator and go through power rule. So 1 over u has a special rule here, natural log absolute value of u. And remember, u is just a temporary variable, so we got to bring back what? Yeah, bring back the x. Plus c, sorry. Okay, example 2. We have too many things going on in the denominator. So we're gonna have to, and also we can't bring that natural log up and it's not gonna, we can't just use power rule to clean up our process. So we have to find a u value that's appropriate. So we have a couple options. Maybe the u value is just the x, maybe it's just natural log of x, or maybe it's the entire denominator x natural log of x. Any guesses as to what our u value could be? So we have to pick a u value where it will produce something that will cancel out the remaining x's in the problem. So we need to have that, we need to kind of play around with this puzzle to figure out what can allow for this problem to transition over completely to be in terms of u. Any guesses for our u value? Natural log of x. If I just pick x, that x is not going to get me any, it's not going to help me resolve the natural log of x. Now, if I did like x equals u and make it 1 over u natural log of u, technically, yes, everything in terms of u, but remember with u substitution, your goal is to make your problem look simpler, right? So if you're just replacing one variable, you haven't made much progress. And if I let my u value be the entire denominator, then the derivative would be product rule, right? F prime g plus f g prime, and that's going to produce way too much. It's not going to resolve, and it's not going to clean up my problem any further. But if I let my u value be natural log of x, my derivative, right? Reminder from first semester, natural log of u's derivative is u prime over u. So what's natural log of x derivative here? 1 over x. Okay, cross multiply. So I'm just replacing those parts. Okay. Make my substitutions. So that natural log of x produces something that will take away that x in the denominator, as we see here, right? X goes away. Do we have a nice rule that we can use? Yeah. Natural log absolute value of u. So it looks a little bit strange here. Natural log of the absolute value of natural log of x. Let me come back to example 3. Okay, this is a little bit more involved. I'll come back to this once we work on an easier problem. So let me skip this one for now. We have 4 additional trig integrals now that we haven't seen before. Okay, remember we have 6 initial trig integrals that came from trig derivatives, but these are special ones that involve natural log. So that's why these 4 were saved until this unit. Okay, so we have 4 of them: tangent, cotangent, secant, and cosecant. I'll go over memorization ways, but for now, we'll just follow the rules. The integral of tangent x dx, this matches nicely with the negative natural log, so I can just apply that. There's a way to derive it to kind of show ways to remember them, but I'll come back to them later. But here, I just want to show that we have these integral rules and we know how to apply it. Okay, so integral of cotangent x dx. This is not one of the original 6. This involves natural log, so natural log absolute value of sine of x. Now, let's go to example 5. Anytime I see a fractional problem with just x's, I'm always asking myself, okay, can I just rely on power rule? What's the issue here? Why can I not just try to clean up and bring the bottom to the top? More than what? Yeah, there's more than one term in the document. It's not that. Now, if it was just x, that's great. I can just bring that up. I can just clean everything up. As soon as I have more than one term, that becomes an issue. Now, how is this setup different than example 1? Do you notice some patterns here? Do you see, what is one main distinction between what we did with example 1 and the setup with this problem? Okay, yeah, multiple terms up top. Something else though. Okay, something else. It's a trait. Compare the degrees. What do you notice? Good. All right, so if the degree is higher in the denominator, typically that's a good fit for U substitution. But if the degree is higher or the same between top and bottom, we have to consider other options because it's not going to quite clean up the way we want to. And if there's numerator and denominator, typically we don't have a change of variable, right? So I'm adding a lot of rules here. But with numerator and denominator, if my degree is either the same or higher up top, we typically go through something called log division or synthetic division. And the point of it is to rewrite this problem in a different form. So long division and synthetic division doesn't solve the problem. It just rewrites the problem in a form that is easier for us to apply the rules that we want to apply. Okay, so let me go through long division steps. You've seen it before, but it's been a while, so this is what we do. Okay. Again, this doesn't solve the problem. It just produces a different version of the problem for us to solve. Okay, so we're dividing by x plus 5. Go ahead and put x plus 5 outside your division notation. And then you're going to put x cubed minus 6x minus 20. Okay, I think it helps if you put this in parentheses to know that this kind of goes together. So you're going to just focus your attention on just the first term here. You're going to ask yourself, x multiplied by what will give me x cubed? X squared. Okay, so you put x squared up here. Now you're going to take that x squared, you're going to distribute it through the parentheses. You're going to put the results right in this space. Okay. So x cubed plus what? 5x squared. Okay. You should always get a perfect match for the first term. Okay. Now you're going to draw a line. And then you're going to change the sign of everything that you just brought down. Okay, so now you're going to add like terms. X cubed minus x cubed is 0. Are these like terms? No, so they all have to come down separately. Okay, but you're just changing the sign of that second line here. The first row, you're not going to change the sign. Now we like to put it in descending order. So I'll put the negative 5x squared first, then the minus 6x, then the minus 20. Okay. Okay, so far. All right, next up, we have to find a match for the first term here. We ask ourselves, x times what gives me negative 5x squared. We only care about trying to find a match for that first term. Negative 5x, okay, good. Now we're done with the x squared, so don't worry about the x squared anymore. We're just going to take what we just put up here and distribute it through our divisor and then put it below. So just distribute the negative 5x through the x plus 5. So what do we get? Negative 5x squared minus 25x. Draw your line and change the signs of everything that you just brought down. The first term should nicely pair up and go away. Now, are these like terms? Yes, so 25 minus 6, 19x minus 20. Okay, then we do this one more time. X times what gives me 19x plus 19. Again, we're done with the x squared and minus 5x. We're just distributing that 19 through the x plus 5. So we get 19x plus 95. Okay, draw your line, change your signs. 19 goes away, and we end up with negative 115. Now, can x go into negative 115? So now the degree is too low, right? We're not able to get a matching degree. So what do we call this? The remainder. The remainder is whatever doesn't divide out any further. So we say plus negative 115 over x plus 5. Now, this is not the answer, but this does produce something that's easier for us to find the integral for. Okay, so then to the side, we're going to present this problem in a different form. So when you go through long division, and I'll show synthetic division tomorrow, is that your first few terms should be easy. So these are all nice power rule. And then the last one should just be a U substitution problem that you can handle with that tsunami. Okay, so these three terms are ready to go. For this one, we got to do a little bit of U substitution. Okay. So just off to the side here, I'm just going to show the steps here. So my U value is x plus 5. My derivative is 1, dx equals du. So I end up with 115, 1 over u du if I push that coefficient out in front. And that's just a nice natural log rule for me to use, right? 1 over u is natural log absolute value of u, in this case, x plus 5 plus c. But the first three terms are ready to go. Those are just power rules. So I'm going to apply each of these antiderivatives. And I did some of the preliminary work for that last term. I'm left with minus 115 integral of 1 over u. We know the antiderivative of 1 over u is natural log absolute value of u. And I can bring that u back in terms of my x. Okay, I have a more efficient way of working through this. I want to show you long division method first, and we'll talk about synthetic division, which will get to this portion a lot faster, but I do want us to know both ways. And the advantages of both ways. Okay, any questions? Okay, I kind of sped through the notes here, but I want to go to some calculator work for your review. You guys can turn to page 6 in your packet. Raise your hand if you are not using a graphing calculator and are using a 36 Pro.
Just today.
Just today, okay. Now, if you're using a 36 Pro, I'm going to show most of the steps using graphing calculator, but I will work with you individually if you're using a 36 Pro because it's not as easy, but it can be done. Okay. Well, I'm just saying up at the point.
No, oh, okay.
I'll let you leave it like that. Okay, so page 6. Okay, so an object moving along a horizontal line, this is a particle motion problem. Velocity is given as 4 sine t squared minus 2 measured in meters per second. We want to be able to graph this velocity function and be able to pull information from it. But also consider this as your velocity, your derivative graph as well. Okay, so in your calculator, make sure that you are in radian mode first off. And then you're going to go to y equals, and you're going to type in your velocity function. Make sure that you always use the variable what? X, that's right. So the paper may show you different variables. And then on paper, you're going to follow whatever variable they're going to use. But in the calculator, you got to make that adjustment. Always just use X. Okay, so 4 sine parentheses x squared minus 2x plus 2. Go ahead and enter that in. Now your calculator, if you just hit graph, it may be, zoomed in or zoomed out, or it may not show you exactly what you want. Usually I like to set my window from -10 to 10. That's my standard window. But here we're going to set the window to this very particular setting. And I want to begin to show you how you can play with the window to zoom into where you want what you want to see. But for now, let's just enter in what you see here. So you're at most, you're only going to play with 4 settings in window. You're going to set your X min, X max, Y min, Y max. That just tells you how far left, how far right you want the graph to show in terms of the X intercepts. And then Y min, Y max is showing you the lowest and highest Y value on the Y axis. So after you do this, then you're going to hit graph. Yeah, don't touch X scale, don't touch Y scale. Those should be setting at 1. Yeah. You guys can help each other out if someone's stuck, but I want to try to walk around too if there's time left over. And then at the end, definitely come up and ask me if you're still stuck with something. All right, hit graph. Now this is your velocity graph. It's nice and centered in a way that it's showing what we need to see. But we only care about the interval from 0 to 4. So I am having you sketch out a little bit more than you need to see. Just for me, I like to see around my edges just to see what's going on. But in this case, we only care about what we see up to that 4. Okay. So how many x-intercepts do you see? Between 0 and 4. 3. Okay. Now I printed this out just to show that graph here, but this is what we're trying to do. We're trying to find those x-intercepts. Okay. We're going to make the calculator do it for us. Now, if you just hit trace, you can trace your way through, but it's not going to be very accurate. Okay. And the AP exam is going to require a bit more accuracy than you trying to get near that x-intercept. Okay. You see that? If you hit trace, you can kind of scroll through and get some idea where that x-intercept is. But we're trying to find a more efficient way, or a more accurate way. So we're going to look for these points. Okay. But the way that you're going to do this, it's highlighted in your on page 19. But I'll just tell you what you want to do. Okay. You're going to go to second trace. And then you're going to select 0. 0 is asking the calculator to give you the x-intercept. So option 2, do you see that 0? Hit enter. Now you're going to see that word left bound. Okay, so left bound, what you're going to do is you're going to scroll not to the x-intercept, but to the left of the x-intercept. Okay, so this one, I'm going to let this be my left bound. It doesn't matter. My goal is the x-intercept, I know, but I'm going to make the calculator give it a left bound to start with. Okay, so you're going to scroll to a point to the left of the x-intercept, and you're going to hit enter. Okay, and that locks in that value for the calculator to start looking. And then you see the word right bound question mark. So now you're going to scroll your cursor to the other side of the x-intercept. Doesn't matter where. And you're going to give it a right boundary. So hit enter again. And then you see the word guess. So what the calculator is going to do, the calculator is going to say, okay, you tell me to start here, you tell me to end here. I'm going to look for an x-intercept for you. It's going to find it for you. Right, hit enter again. I bet. Let's go. Did you get 2.463? Okay. Now, your y value, it may show something strange like this, negative e to negative 13. That's just basically saying it's really close to 0. I wish they would just round it to 0, but that feels confusing. But that's basically your x-intercept, 2.463. Now, if you put your cursor directly on the x-intercept, or where you think x-intercept is, the calculator is going to be confused because it doesn't know which one is left, which one is right. So you want to give it plenty of room for it to find it for you. So don't try to find it for the calculator. The calculator will find it for you, if that makes sense. Okay. So you're going to be doing this 3 times, once to find each of these x-intercepts. Okay, so let me walk around real quick to see, are you guys having trouble getting to these x-intercepts? Reset something. Scale with. Oh yeah. Let's go to. Yeah, I just around that. Oh no. Anybody's not having any trouble getting this?
Oh my gosh, I feel like we're more than some.
Why want to get time of that function? Both sides. Let's get things.
Wasn't like two pages. Oh, so you're not stupid.
X squared minus the function 2x plus 8. Yeah, right here. Negative 1 divided by 7. That's x negative.
Thanks, I appreciate your.
One and minus. Right here, look at your time.
Oh, no, these are short.
Yeah, just go to the, yeah. Yeah, exactly.
And lenders. And. You don't know. No.
It's gonna change your X min have flags. That's your.
Yes.
Okay, are we able to find these t values, these x values? So, I just want to go ahead and create a velocity sign line because that will help us solve all the problems that's related to this. So go ahead and create your velocity sign line. So I'm starting at 0, I'm ending at 4. Okay, obviously you don't have this graph in front of you, but you can just go ahead and put this under part A. Now we pick off the x-intercept because that's where velocity is 0, right? Anything that's above the x-axis means velocity is what? In terms of the direction, right? Velocity is moving to the right, right, and anything below is moving to the left. So what's happening between 0 and 2.463? It's above, so therefore it's moving to the right. Yeah, so you can put a plus here to indicate the direction of motion. And then what's happening between 2.463 and 3.298? It's below, so left. Okay, next. Above, so right. And finally, yeah, we don't care about this portion, right? We're just looking at that little region here to the left of 4, but then to the right of 3.908, it's slightly below. So a lot of information you can gather just from the sign line. You know where the object is motionless. You also know where the object changed direction, right? Where does the object change direction? At all these points, right? Because there's a change in what? Each signs, right? It's moving right, stopping, moving left, stopping, moving right, stopping, moving left. And if I ask you for interval moving right or moving left, you can just also pull your intervals from this, right? You have 2 intervals of moving right, 2 intervals of moving left. All right, so everything that you need, you can just pull from this velocity sign line. Okay, so we're going to go ahead and fill out our A and B. Right, we know where the object is motionless, and because of the sign line, we also know where the object changes direction because velocity changes signs. Part C says find the velocity of the object at t equals 3 seconds. Well, we have the velocity function stored, right, under y. So what you can do is you can just call the function and let it insert for you. Someone in my my sixth period class showed me a shortcut to the vars, y vars, getting to that feature. It may not work for the older calculator, but if you do alpha trace, sorry, yeah, go back to your home screen. Go back to your home screen. You see alpha trace, it pops up all the options for you, and that's a lot faster than what I was doing before. So alpha trace. So alpha trace, you can select Y1. And now just hit parentheses 3, and it's going to insert 3 into this velocity function for you, and it's just going to give you a numeric approximation. So that's a lot faster than having to plug it in by hand, and also to find that vars1, that feature that I was doing before. Okay, so velocity is negative 3.836 meters per second. So again, alpha trace will allow you to select from your y variables that you have stored that you want to use. All right, next up, find the acceleration. So what's the relationship with acceleration to velocity? It's the what? Derivative, right? So we have a derivative feature on our calculator. So if you go to math 8 is n derivative. So d over dx, again, you can call that function. You don't have to keep typing in the velocity function to alpha trace y1. But I'm trying to find the derivative and insert a value in. So I got to plug 3. So I'm basically making the calc do all the work for me. It's finding the derivative and it's inserting that 3 for me to get that slope, to get that velocity value. And what's the unit of measure going to be for acceleration? Yeah, meters per second squared. Okay. Okay. Next up, part E, is the object speed increasing or decreasing? Well, from first semester we learned increasing, decreasing speed. What do? We compare that signs of velocity acceleration, right? So if one is positive and the other is negative, what does that mean? Speed is decreasing. Yeah. Okay, next up. And the reason is because velocity is negative and acceleration is positive. I talked a little bit about this last time. Total displacement. There's a distinction between the 3 things that I want you to make sure you're clear on. Displacement versus position versus distance. Displacement is just how much progress did I make from where I started to where I ended up. So it's just the integral from a to b of v of t. So we have that definite integral feature in our calculator under math 9, f an integral. So you're just going to go from 0 to 4. Again, call your v of your y1, which is stored under, we do alpha trace. So we know that in this time interval, this object is going to make a forward progress of 7.753 meters. Okay, part G, find the total distance. Okay, so total distance is absolute value, right? So definite integral, the absolute value of v of t. On the test, I'm going to ask you to write out the notation. So make sure you put absolute value just around the v of t and not around the entire expression. Okay, around the interval. The integral is just around the v of t. So again, go to math 9. Definite integral from 0 to 4. Now, the way you call your absolute value function, you're going to go to math number. Okay. So go to math number, You see that ABS there? That's your absolute value feature. Some of the older calculator doesn't have that absolute value, you just say ABS, and then you can type in alpha trace. It may take a little bit longer for the absolute value for the total distance to show up. Okay, we'll skip H and we'll skip L. We'll just do two more here, J and K. So J, it says, given x of 0 equals 2, find x of 4. So this is a little bit different, right? So let me again talk about the distinction between these three ideas here. Displacement just means how much progress did I make comparing with where I started to where I ended up. I just want to know how much distance is there between where I started and where I ended up. Total distance is, if I'm going forwards and backwards, I'm just counting my steps. How much movement did I make in that entire time interval? And any movement I make, I'm going to count it as a positive value. So forward 4, backwards 8, I'm going to count it as positive 4 plus 8, which is 12. Final position is saying, okay, let's say you started at this location and you traveled this far. Where on the x-intercept are you going to land if you were to start at this point and you were to move this far away? So final position is actually asking what's the physical location that you're going to end up on this x-axis. So that means I need to have a starting point plus the amount of progress I'm going to make. So if I add those two together, I'm going to be able to find out the physical location I'm going to end up at my ending time. So x of b equals x of a plus. So I want to find the location 4 seconds in. I have where I am at 0 seconds. And so all I want to do is figure out how much progress did I make between those time interval, and I'll add it to my starting location. So I started at 2. I made a forward progress of 7 units. So in the end, I'm going to end up around 9 on the x-axis, because I started at 2 and I moved 7 units to the right. That's right. This one does not have a unit because it's just asking for a location on the x-axis. But if you put a unit there, I won't complain. Okay, and then finally, part K says find the average velocity. So average velocity is average value theorem. So average value theorem, we just go through the formula. 1 over b minus a, 0 to a to b of our function. So 1/4, my a is 0, my b is 4. So 1/4 of the depth of my displacement. So I already have this value, 7.753. So I just take this divided by 4, and I get 1.938. I'm looking for average velocity, so that's why my units will still be meters per second. Okay, so if you're having trouble with any parts that we went over, I want to come around and help you, so you know. Yeah, so H, I, and L will not be on the test, so we don't have to do those. Just the ones I went over for you.
Yeah, be like it.
So, so just be.
You think we can put that because
Oh.
because it's one and one.
So what were you plugging in?
So if I want to plug 3 into the function, I would do parentheses 3 and I'll do that down. But then if I want to do integral function, I need to add that. Okay, this is a little bit, you have a one or?
Yeah, I have one.
Okay, so let me show you quickly. This is. All right, tomorrow we'll continue with, additional notes. No homework, okay, so homework, I just want you to prepare for the test. The homework I'll push to be due Monday. To be due Monday. All right, come up and get your phones.